So now let's talk about how silicon chips actually work. Our story starts back in the 1930s with this guy, Claude Shannon, who published what's arguably the most important master's thesis ever. Claude Shannon's probably more important for the modern world than Einstein. Einstein's work is very theoretically elegant, but hasn't had anything like the impact on our world today. Now, Claude Shannon had an unusual background. He'd done a double degree in maths and electrical engineering, and he was able to combine what he'd learnt from the two halves of his degree. In maths, he'd learnt about Boolean algebra, which is basically a mathematical way of doing logic puzzles. In engineering, he'd learnt about switches, electrical switches, and what he realised was that by combining electrical switches in complicated ways, you could do Boolean algebra. You could do any sort of logic puzzle. The basic idea is you have a wire with a switch somehow in it, and whether the switch is open or closed, whether it allows the electricity through, depends on the voltage on a separate circuit. And what you can do is you can feed the output of the switch into another switch and into another switch and build these incredibly complicated networks of switches which can do Boolean algebra, can do any sort of logic puzzle. This was extended further by his contemporary Alan Turing in the UK, who showed that basically if you could have any system that could do adding up, subtracting, plus have some storage, so store values in a memory, you could basically do any calculation, any operation. This is a Turing machine. So all you needed was the ability to do Boolean algebra basically, and some storage, and you've got a universal machine that can do almost anything. Both these people worked as code breakers during the Second World War and actually put their ideas into practice. Now back then the electrical switches were vacuum tubes, like all these ones over here. Basically you got a glass bulb with the air pumped out, you had a filament that radiated the electrons into the vacuum, they would be accelerated by a grid until they hit a plate, thus causing the current to go through, and by changing the voltage in the middle you could turn it on or off. So this was an electrical switch, and you could build computers out of lots and lots of these. And here indeed is what many people argue is the world's first programmable computer, ENIAC, computed during World War II to calculate artillery tables. So they wanted to calculate if you fire a projectile in a given wind speed, in a given direction, how far will it land, that the artillery people could use to actually set their guns to hit the targets. Previously these had been done by large numbers of people writing down calculations over and over and over again. You have rooms full of people just doing by hand calculations, but that was error prone and very expensive. People also used mechanical calculating machines, but this was way faster. It had 18,000 vacuum tubes, 70,000 resistors, 10,000 capacitors, all of which had been connected by hand. There were 5 million hand-soldered joints in the entire thing, so just imagine how many years it took to build this thing. The total weight was 27 tons, and it typically broke several times a day just because one of these 18,000 vacuum tubes had burnt out. They eventually got more reliable vacuum tubes, and it only burnt out once every 2 days or so, but nonetheless reliability was not its strong point. But when it was working, it could do a whopping 500 floating point operations, like multiplying two long multi-digit numbers together every second, and humans can't do that. So it was very useful. But it was clear that if we relied on vacuum tubes, it was never going to get much beyond this. So the really crucial advance was the use of silicon, semiconductors. Now, of all the substances on Earth, they can be divided into conductors, things where electrons can flow freely backwards and forwards, so electricity can pass very easily, like most metals. Insulators, like glass or woolen jumpers, where electrons can't move. And then there are the rather curious semiconductors, which are part way in between. And what we know from quantum mechanics is that in semiconductors there are two energy levels which electrons can be in, what's called the valence band, a lower energy level, and a conduction band. And one of the many weird things about quantum mechanics is the electron can either be in this band or that band, but not anywhere in between. So normally if you have a block of pure silicon on your desk, the electrons, I've shown them as blue circles here, will all be in the valence band. Now if you try and apply a voltage to this, nothing will happen. there are no electrons up here in the conduction band that can move, and down here in the valence band there are lots of electrons that would like to move, but there's nowhere to move to. Every possible position is already full. It's like you're standing jammed in some huge crowd of people and you just can't move anywhere no matter how much you want to because you bump into somebody. It's not quite that bad. In reality, a piece of pure silicon will every now and then occasionally have an electron that's been knocked up to the conduction band and is therefore free to move around. This is usually because just of heat. At room temperature, all the atoms are jiggling about because of the random thermal motion, and occasionally that will knock an electron all the way up from the valence band to the conduction band. It can also be caused by light. If you expose some silicon to sunlight, a photon of light will sometimes come in and knock an electron up, and this is indeed how charge-coupled devices, the detectors used in most smartphone cameras, work. They're basically silicon where light coming in and hitting pixels knocks electrons up to the conduction band. But the conductivity is pretty low. There are only a few electrons free to move. What you can do, however, is dope your semiconductor. There are two types of doping, P-type for positive and N-type for negative. The basic idea is instead of having pure silicon, you put just a small number of additional atoms, typically boron or indium or something like this. And these are atoms where they have just the outer shell of the electrons, for those who remember their chemistry, isn't quite full. It could do with having one more electron to fill it up and we're much happier then. You may remember this from covalent bonding. And so what happens is one of the electrons that's in the valence band, instead of sitting there, gets sucked away to fill up the outer shell of your boron atom nearby. And what this means is that you now have a gap in the valence band, a hole. Now if you apply an electric field, what happens is, if the electric field is pointing in this direction, the electrons want to go the other way. So the electron here, that one can move, it'll move over there. And now this one will move to the side. And they'll keep on moving. So what's effectively happening is a hole is moving in the direction of the electric field. What's actually happening is electrons are moving the other way to fill up the gap, but that's what it looks like. So in P-type semiconductors, charge can move, and it looks like a positive charge moving around. It's really just a hole, and the negative charge is moving, so the gap appears to move in the direction of the positive charge. So that's P-type semiconductors. There's also N-type, negative semiconductors. Here you dope with tiny amounts of some element like phosphorus or arsenic, and these are elements which have just one electron in the outer shell, one poor lonely electron that wants to escape. And so that electron will often wander off, leaving a residual positively charged phosphorus atom, and that means that while the valence band is full, you get a few spare electrons in the conduction band, and these few spare electrons are free to wander around. If you have an electric field, they'll run off in one way. So both of these things turn silicon from a rather pathetic conductor to a rather good conductor. There are charges that can move around, either holes or electrons. How does that help you with the switch you need to build a computer? Well, most current computers, there are several ways in which semiconductors can do this, but the most common way is what's called the Field Effect Transistor, which works something like this. Basically, you take a piece of silicon and you dope it differently in different areas. So in the middle it can be P-type, and in the ends there can be a bit of N-type. Or the other way around, but let's run with this for the moment. Then you deposit a layer of some insulation on top, typically silicon. You oxidize it to have silicon oxide, which is an insulator, and then you put a piece of metal up the top, which is the gate. So you've got a source on one side, which is the N-type region on one side, a drain on the other side, and the P-type in the middle, and the gate. Now let's say you apply a voltage between the source and the drain. The electrons would like to flow from one to the other, and the holes in the middle would like to flow the other way. But they can't, because as soon as the electrons get into the P region, they will fall down to the valence band and fill up the holes. Likewise, if a hole comes to the N region, it'll be filled up by electrons. So basically, nothing can happen. In both areas, the P and the N type, the charges want to move, but as soon as they hit their boundary, they're just mopped up and they can't. So no currents flowing. But you've got the voltage here, and you apply a strong positive voltage, what happens is there are a small number of just freely wandering electrons in even a p region, and those that all get sucked up to the top, they'll be attracted to the positive voltage up there until you get lots and lots of electrons. What this means is that a very thin layer at the top, just underneath the oxide, first of all the holes will get filled up by these electrons being sucked up to the top, and eventually you get so many electrons sucked up to the top that actually they become surplus. They fill up all the holes and there is some left over, which is effectively turning it into what's called the inversion layer, a thin layer of N-type semiconductor on top of the P-type, which now means that the electrons can flow all the way through. So by applying a voltage here, you've created the inversion layer, you've opened the gate, and you've allowed the electrons to flow. So you have your switch.